All right, welcome back, everyone. I hope you all enjoyed the coffee break. So we're about to have the second part of Frank Zhang's lecture on machine learning approaches for condensed matter systems. Let's all welcome Frank.
Thank you. So in the last lecture, I briefly covered how machine learning techniques such as artificial neural network offers an alternative way of programming and doing regression, especially nonlinear regression, and to recognize the classification and the universal patterns in certain input, especially inputs with huge amounts of data. For example, one of the examples is that the image recognition. Let's say you have a handwritten digit of 1, which is the handwritten one, not the perfect Times New Roman type 1. So everyone has their own style of handwritten 1, but there got to be a universal rule describing the simple principle after what kind of thing is a 1, like you will be teaching your kids and your kids, future kids. Like this is 1, it's just a straight line or something. But how artificial neural network will be doing it is get a huge data set containing all different paintings of 1s, and train a neural network, basically the connection and the bias, connection, the weight of the connections, and bias on each of the neuron to adjust their each individual firing condition. They each act independently, but their collective kind of effort will eventually give you the result that this is actually a digit 1. So with this kind of problem that has been nailed in the past decades, one immediate thing to ask is that whether this kind of algorithm can apply to condensed matter system. After all, one of the central goals our condensed matter physicists are asking ourselves are, well, given a Hamiltonian, given one wave function, given a state, what kind of quantum phase or classical phase this is describing? So in 2017, there was one very illuminating example by Wang and Roger Melko. And what they did is that they considered the classical Aizen model. So the model is classical because all of the terms in Hamiltonian communicate with each other. The Hamiltonian is just a bunch of spin 1/2 on a square lattice. And each sigma can take value plus or minus 1. And the overall energy for each spin arrangement, spin configuration, is simply given by J, which is the nearest neighbor spin coupling, times the product of the nearest neighbor spin. So this bond over these bonds. So this is the 2D classical Aizen model that has been very well known, and we all know there are two corresponding phases at higher temperature and low temperature specifically. At a really low temperature, the spins are really keen to be aligning with each other because that kind of minimizes the energy. And we have a ferromagnetic state. And when temperature is higher and entropic kind of effort wanes, and the spins are free to arrange in random kind of pattern, and we have a paramagnetic state. So this is and also due to the duality of this problem and the transition temperature for this simple problem is also very well known. Okay, so given this problem, and we know there are two different phases that offers for us two distinctive outputs that we can have given the input. Now the question to ask is, what is the input? Well, what Wang and Roger figured out is that they decided to use the Monte Carlo samples of the spin configurations as the inputs. So if you're not familiar with is a Monte Carlo sampling, then it's in terms of classical systems, so the probability of a given spin configuration to appear is e to the minus beta times probability, that's of course divided by the prediction function, that a specific spin configuration is going to appear. Okay, so if this is the case, then we can design a sampling scheme which is usually called metropolis. And it only needs to satisfy two rules. The first rule is the detail balance. And the second rule is periodicity. So what is a periodicity is that given that many spins and you have a huge Hilbert space, but you have to you propose an update like between different configurations so that all of these states in Hilbert space is in principle possible to be visited. So that's the periodicity part. And this can be easily realized by proposing like so starting from one configuration, and then you can randomly select the spin and ask whether this spin is going to flip or not. And this simple kind of update, if you just accumulate over a long Markov chain or a large number of updates, is enough to guarantee the periodicity, because in principle there's no, we do not restrict which spin is going to be flipped. And so the update will allow, in principle, from one configuration to any other configuration within the entire Hilbert space. The detail balance is realized in a more elegant way. The detail balance will ensure that all of these configurations are going to appear with the wanted probability or weight. The way of doing that is to, when you propose an update, let's say from the sigma configuration, sigma I configuration, to the sigma I tilde configuration. Okay, let's say you just update one spin. Then you calculate the energy difference between these two configurations. And as we can tell from the ratio, the probability or the weight between these two is going to be, so the weight of Rphi versus the weight of Rphi tilde is going to be E tilde minus beta times delta E alpha minus alpha. Okay, so that's the relative weight between the two. And now if we propose this update and accept this update with the ratio with probability with probability that 1 if this value is larger than 1, and so this and that space right here. So we can define probability equals 1 if this ratio is larger than 1, and we'll take this ratio for the update probability otherwise. Okay, so this is the detail balance. So given two states with an energy difference delta E, the chance of going from one state to the other one is this ratio, while the chance of going back is 1. This will ensure that at least the update between the two will obey this weight, this probability, and if you ensure that all updates obey this detail balance, the overall weight will be automatically satisfied. So that's how Monte Carlo, which is a famous town of casino, casinos are built on chance, and the Monte Carlo method is also built on chance. But if we ensure the detailed balance also based on chance, then if we look at the microscopic scale, it's going to give us the sampling that obeys the macroscopic rule of thermodynamics. Okay, so what Ryan and Roger did is that they write down such an update scheme and they generate samples. They generate samples at the extremely low temperature and extremely high temperature. Right here, and right here. Okay, so that kind of tells, so for physicists, we all have these limits that we're comfortable with. Let's say very low temperature, then temperature is almost zero, and the cost of creating spin flips with respect to the thermal activation is very, very small. Spin tend to be aligned with each other, so we have very few spin flip domains, very few disorders. And while for the higher temperature, let's say take the KBT is infinite, then J doesn't mean anything. We're actually dealing with a thermal fluid that without any kind of Hamiltonian. So each spin independently can be regarded as random. So these limits are limits that we're comfortable with. And how it happens in Bitcoin is the interesting questions that we usually want to address. And what Roger Melko and Wan did is that they take the Monte Carlo samples of the Hamiltonians with the KBT, the temperature at very high limit and very low limit. They take these snapshots of Monte Carlo samples, like for example, some of these and some of the more disordered spread array of spin configurations. And they directly use these spin configurations. For example, upspin is a 1, and downspin is a 0. Just like in image recognition, if you have your handwritten over a pixel, it takes a value of 1 or otherwise 0. Use this as an input and train with the corresponding phase. And once you train such a neural network, and then use the neural network on samples generated in between. Okay, so that's an example. And take a J value, KBT over J value in between, generate another bunch of samples, and even maybe just one sample. And use that sample as an input and look at the output neuron. What does the output neuron say? Is a neuron corresponding to a ferromagnet phase fired, or is a paramagnet phase fired? That directly tell you just by one Monte Carlo sample that your phase is going to be ordered ferromagnet phase or paramagnet phase. So the result is pretty astounding. Okay, so for their phase diagram, you get a pretty sharp transition as denoted by the artificial neural network. The neuron output corresponding to the ferromagnet phase just drops sharply as KBT, and right across the transition temperature, KBTC, while the neural output corresponding to this is neuron outputs. When the neural output corresponding to the paramagnetic phase just increases, and we can see the sharp kind of feature over here. And one question is that why it actually doesn't do perfectly near the boundary. Yes?
Yeah, I had a question about your training. Is the training done? What happens if the training is done at very far off temperatures, away from TC?
It is done from far apart temperatures. Yes.
And if you can still find the.
Yes. That's a very good question. There are a lot of detailed ways we can actually improve the behavior of artificial neural network. As we can imagine, if we include more practical examples closer to TC and into the training set, and the behavior of the artificial neural network will also be improved because it gets to have more knowledge about what's going to happen closer to the transition temperature. But all in all, you can get the transition temperature right, and for a classical system, and just by snapshots in the Monte Carlo, it can tell with good accuracy that whether this is from a temperature above or below the critical temperature. So all in all, this is very good. But now the major problem comes when we want to go one step further. Okay, so we want to do something we all like, that is a quantum antibody phase, or condensed. So let's say you have a quantum wave function, or you have a Hamiltonian, and you're proposing the ground state, this quantum state is the ground state of your quantum Hamiltonian. And one most important question is that the corresponding phase for that. But if we want to do what Roger and Juan had did, then the immediate problem is that we can still use the output, the neurons to describe different phases. But what's the input? Okay, so we know that for a quantum state, the quantum state can be written as summation over different configurations. This is quantum state. Alpha is some specific configuration, let's say spin up and spin down configuration. But quantum state is a coherent linear superposition of these with certain coefficients. How many coefficients do we have right here? It's exponentially large. Let's say you have n spins, then the total overall C alpha, number of C alphas is 2 to the n. That's a number way too big and to be used as the input. And even for artificial neural network, there's no compromise that we can handle exponentially increased number of degrees of freedom. So using C alpha as an input is kind of unpractical. So what is the next bad thing? So that's actually. So I'm going to let you know one example here. There are many ways of actually extracting the relevant quantum information out of the quantum states, but here's one example. This example is to use operators as an interface. We know by operator acting on a quantum state, what we have is a C number. C number is more compatible now with artificial neural network. And that can give us desired outputs. So in other words, this thing is called feature selection. So we need to choose operator. Okay, so this idea was done by. Okay, so this is a feature selection. In other words, we choose a bunch of operators, and it's not randomly chosen operator because the space of all operators is just as intimidating as the Hilbert space itself. But choose a wide selection of operators. Use these operators as a feature selection layers or interface. These operators act on the state and extract the information we want out of it related to the question we will be asking, and pass this information to an artificial neural network, which is still a classical artificial neural network. And then you can, once this kind of logic, this connection is complete, then the training out, the logic training and then applying in the neural network just straightforwardly follow. So one important question we can ask is, okay, given a state, how do we actually value an operator, right? So for example, as Leon has mentioned yesterday afternoon, so there are many trial wave functions. Many of the trial wave functions you can write them down, like projected wave function, partial wave function, etc., etc. But given a wave function, okay, so how do we get the value of an operator? Well, this can be done also in the framework of Monte Carlo. I mean, of course, if this wave function is a direct product or something, or then things can are considerably simpler. But in general, there's still some work to be done. It can be done like in the following way. So this method is called the variational Monte Carlo, by the way. So it's called variational Okay, so what we want is that we want to evaluate the operator, the value of operator. Okay, so and to do that, this wave function is a many-bounded wave function. We can introduce a bunch of identity operators. And the denominator would just be normalization. Okay, I haven't done anything yet. And now I'm going to separate this value into two parts. That's this denominator. In the numerator, I'm going to do a trick so that I'm allowed to separate into two parts. I like two parts. Times beta 1. So basically, I just took up two copies of alpha phi on the denominator and numerator. But what you can realize is that this first factor right here, it's a positive definite probability. So what I mean by that is that this thing is always not larger or equal larger than zero. Larger than zero. So it's a non-negative property and normalized. By saying normalized is that if I sum over all possible configurations of alpha, this average, this sum up to 1. So this thing can be regarded as, just like the case of a classical Monte Carlo, as the ratio for this specific quantity configuration alpha to appear. So this is just like for our classical configuration, the corresponding probability for, or weight for now this cat or bra, this configuration alpha to appear, while this thing, which has the operator itself in it, is O, alpha. In other words, we have broken down the evaluation of the operator into a statistical average with this as the probability and this as the value of the operator at that specific instance of Monte Carlo sample. Okay, is everyone still with me right here? Okay, so what's good about this method is that if you want to measure one operator, you're going to do this Monte Carlo sample anyway. But if you want to measure, let's say, a bunch of operators, you can just use one, still use the same Monte Carlo sampling corresponding to alpha, and it's just like we can measure, let's say, O and Q operator, O3 operators at this Monte Carlo instance. So we take a snapshot, and at that snapshot, we can get the values contributed by that snapshot to many operators at the same time. Okay, so that's one way of saying we can take a snapshot, we can get the Monte Carlo sample of these operators. Okay, once we have that, we have finished half of the problem. We solved half of the problem. So we know if we knew that which operators are important to the problem we're asking, and we know how to sample them, we know how to evaluate these operators very efficiently. We can get also many samples as well. But now the central question still remains, which is, okay, so what operators we're going to use, what O's are we going to choose for this purpose? It cannot be a random operator. So how do we cope with that problem? So if we're doing a randomization group, this is a trivial question because we know the answer already. That will be the coefficient of the random operator. But unfortunately, we're not doing randomization group, and we are also not dealing with an IR fixed point theory. And we have the lattice in general. So what do we do with? How do we deal with that? Well, so here is actually what I call use a lot. We'll take a lot of intuition and compromises. So this is the what we call a Cornell topography. So you're asking a question. So yes, pulse. QUANTUN quantum loop TOPO over GRAPHY.
What's the tomography?
Topography is like the equal the format. Okay. Okay. So what this is actually just a bunch of operators that's wisely chosen so that they can act as our interface. So here, let me show you an example of human learning. So what I'm going to do is I'm going to show you examples, and maybe you will learn how to actually write your own version of Cornell topography, given the state of your own interest. Probably. So the example I'm going to show you is a lattice model of anomalous chain insulator or fractional chain insulator. And okay, so now we have this problem. You have a wave function, a series of state that interprets, let's say, a chain insulator. Or more commonly known as quantum anomalous Hall effect versus trivial insulator. What I mean is that something which is adiabatically connected with a target limit. Okay, so or fractional one. So if you're handed a problem like this, okay, so what we can help and ask what we want some operator that's related to the distinguishing between these two operators, these two phases. And now we have to ask random questions. So what is the major physical difference between a chain insulator or a trivial insulator? Okay, so they are topologically distinctive, but they also have very distinctive response theories. So for a trivial insulator, it doesn't have any sigma xy, and doesn't have any sigma xx, and doesn't have any whole response sigma xy. But for a chain insulator, it has a quantized sigma xy contribution. So for this thing, it has E squared over H, whole conductivity, or whole conductance, same thing QD, and 0 for trivial insulator. So that kind of question you can ask for many other states, such as the superconductivity versus just trivial metal, or you can ask for some type of topological quantum field theory versus not topological quantum field theory. But ask for the feature that distinguishes the two. And now, I can tell the whole conductivity is different, but I'm not going to evaluate that because that will be cheating. That's just like the normal way we do physics. And let's say we do not know how to measure that eventually, even. Okay, so we only have a state, we don't have a Hamiltonian, remember. So we cannot evaluate sigma xy because we do not know the excitations, we do not know the energy of the excitations and the states of the excitation. So evaluating that is not an option, but we can still get information out of it. So what do we do? So then we ask what operators contribute to this type of response theory, or whatever features you decided to focus. So what operator contribute to current correlations, etc. Well, okay, so I'm going to show you that sigma xy for a non-interacting free Fermion problem can be eventually broken down into two-point correlators, two-point correlation functions. So to do that, let's start with a Kubo formula for sigma xy. Okay, so Kubo formula tells us sigma xy is I squared hr divided by n, which is the number of sites, summing of the number n, where v is the single particle state in the valence band, and m is in the conducting band, or in the unfilled band. Okay, that's the Kubo formula. So here is one trick I want to do. So Vx and Vy are Hamiltonian related stuff. It's not generic. So I do not wish them to appear in the Hamiltonian. And especially given a state, I do not know the excitation spectrum generally. So I do not want this to appear. So here's what I do. Another intuition. So what I want to do is that, okay, so by looking at this, and then I want to see if I can replace Vx and Vy with something more generic. And there's indeed one way of doing this. So we know if we have a non-interacting Hamiltonian, this part. And I can calculate the two-point correlator. Sorry, I have the ground state. Okay, so if I have the ground state, sorry, I can write down a projection operator that project this. If I have an antibody state, I have a ground state wave function. I can write down a projection operator into that state. So in terms of that language, it's just this. Okay, so it's a summing over all the occupied single particle states. That's a projection operator. So here is a claim that if I write down a Hamiltonian, which is just minus delta p, it will have the same topological property as the original H that will give me this non-interacting ground state. To see that, so P, this H prime, and the original H will have the same ground state, right? Because this is sure because P is a projection operator, and the eigenvalue of that will be exactly just occupying all M. And also, the energy spectrum is that for a state, single particle state that's within the valence band, the value for H prime will be minus delta. And if for a state which is not within the valence band, then the Hamiltonian will, this effective Hamiltonian will return 0. So in other words, this H prime will give you a flat band. And for all the states, single particle states, that's not in the original antibody wave function. The energy is 0. The energy is 0, and yes it is.
Frank,
Yes.
what is delta?
Sorry?
What is delta?
Oh, delta is arbitrary C number. Just it's a parameter. 1. You can take it to be 1 because eventually it will not affect the physics. And for spinning balance band. Okay, so that's good. And the second thing is that I'm going to put an argument here. P is an operator, and the P operator transversed inside I and J for the single particle state is just a 2-point correlator spanning inside I and J. Okay. Using this as a fact, I can simplify this expression significantly. So I'm not going to calculate sigma xy for the original h because I lack information about h. But I'm going to calculate sigma xy for this effective h prime because I have believed that they're actually in the same phase. So for Vx, for example, Vx prime, then this is just h prime, x. The commutator between this effective Hamiltonian and x, okay, and it's just I delta divided by h prime p x. Okay, so I'm going to. So now what I can do is I can put everything inside, but not for original h, but for h prime. Then this excitation spectrum will be trivial because all the excitation has energy, single particle excitation has energy delta. So this thing becomes minus h prime and c over. Okay, so summing over. Let me use trace instead. So for M, it's in the valence band. So it's a projection operator into valence band. Then Bx, as we have shown, Bx just P x. Of course, that times delta. And for By,
Right.
yes,
There are a lot of P's.
they're all the same.
Pij
Pij.
and the projection P are not the same.
Actually, for single particle states, if you want the projection operator into the ground states, so the way of getting that projection operator is to calculate in your ground state 2-point correlator. In other words, if you hand over a free non-interacting fermion problem, you want to get a projection operator, let's say the flat band Hamiltonian. The easiest way for you to get that is just to calculate the 2-point correlation function. And that 2-point correlation function spanning side I and j, and you just summing over side I and j, is already a Hamiltonian that gives you a flat band. So that's in other words, this is actually an operator, but this is an operator in the representation of real space. Okay, so. Okay, so remember all of these are operators. So if I eventually choose a representation, that will be a matrix. And minus x and y changing. And there's going to be a delta here, but I also have delta squared in the denominator, so we all cancel. Okay, so we're getting to the results. And what I can do is here's a trace, I can actually put my real space indexes here. So JK, so for example, PJK and PKL, PLJ, because it has to be traced, then the tail has to come back to the head. And for that, eventually, it's going to be E squared over H, M squared over N, and times summing over all JKLs, and that's PJK, PKL, PLJ. Times the area of the triangle KKL and for pi. Okay. So what I've shown is that I proved for the non-interacting case And sigma xy can be expressed in terms of two-point correlation functions, and the contribution will be also proportional. So these are operators, okay? And the contribution will be proportional to the area of the triangle. And in order for this one to be exact, I need to sum over all the triangle ijk, and even for those ones which are really as big as the system size. So the triangle ijk spans over the entire lattice or space that you're calculating. And it's the imaginary part which that contributes. There's a 4 pi I right here. So, but why I'm doing this? If we remember why I was doing this, I'm just looking for the operator that's most important for call conductivity. And I'm not telling you whether I want to start studying an interacting problem or not, but I'm just trying to work as a physicist and use a lot of approximation. So now I do everything that's not generic. For example, S delta JKL is not generic. I can change the symmetry of the lattice, etc., the length of different bounds. That's going to change. But it's kind of telling me that this operator is kind of important. Okay, so this operator, two-point correlated trading a triangle, is very important when we're talking about something related to sigma xy. So these can be used as my O's. And remember, it's not just one of these operators. I can define a triangle spanning jk, size jkl. I can define another one spanning size j prime, k prime, l prime. So there's going to be a whole lot of bunch of operators. However, we can again use some intuition. Here's the intuition, and you can judge whether it makes sense or not. I'm going to claim that only the triangle of smaller, relatively small size is going to be important. Why this is the case? Remember, we're dealing with insulators. No matter it's a chain insulator or it's a trivial insulator, it's going to be an insulator with a sizable gap. So if we're asking questions related to that, correlations are all exponentially decaying in these problems. And although the area corresponding to this is actually parallel increasing, nothing beats exponential decaying. That's kind of telling me the most important operator are actually those which is so minimally non-local. So they're triangles, they're not completely local on site, but they're also not the largest one because the correlation over large distances are just negligible. So now I'm going to focus on these operators spanning some of the smallest triangles and make a truncation, saying I'm just looking at the smallest triangles. That's the first approximation we're going to make. The second approximation I'm going to make is that I'm going to study the problem which is laden with quantum fluctuation. So remember when I talked about how to evaluate operators, which I put for is right here, okay? The true way of actually evaluating an operator is to take a weighted average over a huge number of Monte samples, and I'm going to let it settle on just one sample. I'm going to take one sample, and on this sample, I'm going to calculate all of these relevant 3-point operators, the 2-point operator trading the triangles, and I'm just going to settle with that. Okay, so I made a whole bunch of approximations right here, just using the intuition. But the hope is that, okay, although this is not the adequate set of information, and it's laden with all kinds of lots of information, for example, truncations, and laden with quantum fluctuations. But if we train with data that's laden with those, it will eventually overcome and know to recognize these are actually unimportant, unnecessary, and think through all of these details to look for those things which is more essential for decision making. Okay, so these are the pieces we're putting together. And we can also do the same thing, but for chains later. So what we do is that we can just train with, yes?
I thought one of your phases had some sort of topological character and would be associated with some non-local order parameter. So I'm just curious how you're getting away with just measuring local quantities.
That's a very good question. So it's not local measurement. It's each operator is semi-local or quasi-local, But actually, I'm not just measuring this operator, but actually I'm measuring operator that spans the entire lattice spacing. So it contains information not about a local point, but also the correlation between these local points as well.
Sorry, then I didn't understand. Those operators were those PK something.
So
I'm sorry, I didn't get that. So the J and K are site indices?
JK and KL and LJ are site indices.
Yes.
So this will give me one local measurement.
Yes.
But I'm not just inputting that.
Okay.
I'm inputting this thing for the same locale sample over everywhere, from the JKL side as well as J prime, K prime, L prime side, which is very far away. All of these are input into the same neural network. So that's a huge amount of data. That's if you have started with a two-dimensional lattice, you get a quasi kind of 3D kind of image because given one side, there are so many triangles associated with sharing a vertex on this side. So you get a 3D kind of figure.
I think the question Hitesh is asking is kind of at a more conceptual level.
Yes.
If you have a topological order, you have a non-local something rather,
Yeah.
right? And what you're constructing looks very local.
Right.
So how do you get some non-local thing that has to know about the entire system out of local things? And I think the answer
That's
is
the question. Like in the AKLT chain, you have product of
right.
LGs all
So
over
so
chain.
the thing is that all this input,
Yes.
this what Frank is constructing
Yes.
forms an input vector
Okay.
that goes into neural network, and neural network handles it in whatever fashion it finds effective to handle it. Most it could be just summing everything, for instance, or it could be summing and summing in powers.
Yeah.
It could do whatever it learns to be the right thing to do. Specifically, it can do nonlinear operations.
Yeah.
So
So in
it
other
could be
words,
multiplying.
in other words, the neural that many things is important here. So one thing is that I have local information from non-local patches. The other thing is that neural network is capable of doing non-linearity. So it will be able to study correlations. That's not just linear yet.
To get a string order parameter, how many layers?
Actually, I'm not going to show that, but yes, it will be able to do products, non-local products.
With a single hidden layer.
It has to
you
have hidden layer, yes,
Yeah.
of course. Yeah, with a single hidden layer, you already have a lot of expressibility. Okay, where was I at? Is that okay? So we can study, let's say, fractional integer phase or integer change later phase. Back to here. So we know we have finished the other half of the mystery. So we know how to evaluate O now, and we also know what O's are important for this specific problem. And then everything goes the same as before. So we take phi's, which is let's say in some example very deep in the phase, very representative of the integer quantities or change leader, and some trivial one as contrast. We can also do the same thing for fractional phases, fractional change later versus trivial insulator. And there it's a strongly interacting phase, but let's just settle with the same set of operators, but because the intuition telling us these operators are equally important for the fractional change later. And once the train is complete, we can do some interpretation and study some other problem that's not some model which is not entirely in the training set. And let me show you some examples.
Can you explain again how does the decomposition in trajectories motivated by the Kobo formula? How does this guide your choice of operators?
Yeah.
Oh, I didn't want to.
No, it's totally okay. All right, so so we want to study something, and now we feel like sigma y is the key, but we cannot evaluate sigma y because we lack information. So we want to start study what operator actually contribute most, what generic operator that's available to all models. Like correlation is generic. So then what you can do is actually start with something with a Kubo formula, but try to look for examples which are more generic. Like that's where I actually talk about the projection operator as the vector Hamiltonian, replacing everything. Now everything in your Hamiltonian, in your physical response theory is generic. And look for those operators eventually, and that's contributing to that. Those are very likely the ones that's actually very relevant, closely relevant to the phase you're talking about. So these are very good junctions. Okay. So these are the features, and I'm doing feature selection. Why this is not coming? Yeah, I think I broke it. The first example I want to show you is a non-interacting example between a trivial insulator and a nonlocal Hall effect. So this is the result. The training is down at 0.1 and 1.0, and we trained the artificial neural network, which is simple already. With just one hidden layer with several kinds of hidden layer neurons. Once the training is complete, then what we do is that we do the same thing. We gather samples, Monte Carlo samples of operators from the intermediate values, and we input these operator values as our input data. And output, that's the output. Output is telling us if it's 1, then it's a chain insulator, and then 0, it's a trivial insulator. So we see that it's generically doing quite well. This is a non-interactive example. So I know the transition point exactly. So the transition point is exactly at 0.5. So for most of the particle region where the gap is sizable, the accuracy can be 100%. It's only near the transition and the accuracy is actually coming down. And we get a bunch of confusion coming up, which is kind of expected, right? Because why? Because when the gap is small, when it's close to the transition, correlation is going to blow up. Correlation is blowing up. One approximation I made is going to fail. That's the truncation. That means the information is actually getting more and more spread out in the triangles I'm throwing away. And remember, for example, here I only consider triangles with linear size equal or smaller than 2 lattice spaces, and throwing out a lot of information. That's kind of expected, but even there, you can see across the transition, there is some sharp non-singularity coming through. So before and after the transition, although the neural network is kind of confused, it noticed just by looking at the smallest triangles that something's going up. Something non-analytical is going up right here. So here is another example. So this is the example is a fraction chain insulator wave function. If you recall the unbalanced lecture yesterday, so this is can be done with Parton construction. You just write down a chain insulator fermions as partons, and then project to the subspace of Hilbert space, where the partons are actually bind together, just as if there's a gauge confinement. We know by very careful studies that the two limits are trivial insulator and chain insulator. But in order to study what's in between, it's a much more complicated task. So here, in this example, we train the neural network with these correlations, training triangles. And then we do interpretation and find transition somewhere around 0.3. There's 3 ground states, so we didn't bother. Yes, is there a question?
Yeah, I think you answered it. Yeah, I was just going to ask, the expectation values of these operators are calculated in which ground state? Are they calculated only in one state or?
3. I think there are 3 different points right here.
Yeah.
So you see that the 3 ground states are shown right here, and we have a transition, and then we calculate, let's say, ground state genericity and the benchmark to see where the transition is happening. This is not exactly solvable anymore, so kind of it's consistent with our what neural network is telling us, is teaching us the story. And yeah, so okay, so that's one example. Let's see, which time I have. Okay, so that's actually very helpful because especially for the topological phase that lacks a very good order parameter, detecting topological phases has always been an issue. So this is a very good contrasting case that artificial neural network, machine learning approaches can actually help us do something, which is which really helped us in a non-trivial way. Of course, there are many ways of writing down operators relevant to the theories that you're interested in, even we're not using operators, there are other things we can use which presumably also contains information. For example, we can use entanglement, entanglement spectrum, or other entanglement techniques to extract pull information out of component states. It's also a very good replacement. It can also be based on experimental data. So you have some disorder system, something. The experimental data routing is just too disordered and had too much fluctuation to deal with. And you can train synthetic data containing all of these, following your hypothesis and manually adding disorder and fluctuation, train the neural network and apply to the real experiment data, etc. There are many ideas following all of these, the use of these artificial neural networks. And it actually has a lot of advantages. For example, the example I showed you is extremely efficient for many different reasons. One reason is that we can circumvent the case where there's no auto parameter to be looking at. Of course, even for quantum phase, if there's a well-defined operator, we can just use the operator as our equivalent loop topography operator. Then it will be very similar to the classical case. But the topological case, this is a game changer. It's also fast in the sense that I don't really need a converged expectation value because it can handle different systems symmetry as long as it's not the things that we're focusing on. Let's say we're just focusing on topological index, not the symmetry it's looking at. And if I do the same training and the square lattice, and once it's finished, I apply on the Kakomi lattice or Hankan lattice. It's going to fail. Really? The reason this is not unexpected because you're not asking the right question. It doesn't know whether it's actually looking at a translator or a topological phase with square lattice symmetry. The right way of doing that would be actually train your neural network with all kinds of representing samples with different lattice symmetry. And then it knows, okay, it's actually looking at the topological phase regardless of lattice symmetry. So if you train with both Kakomi and honeycomb and let's say square lattice, etc., and it would be even better if you just add disorder to break as much symmetry as possible, since symmetry is irrelevant to our final phase recognition. And then it will recognize the phase regardless of your lattice symmetry. It can be as diverse as that. And of course, there's no need to converge to the expectation values for the operator. So just give me one snapshot of your operator sample value. It's going to tell me whether it's the phase you want or not. And you can also handle different topological phases simultaneously. Just add more output neurons. It won't confuse between different topological phases. We tested all of those. So yeah, I think there's still a long way to go, but most importantly, once we train this neural network, and we're up to a stage where we actually start understanding. So this is like a function. You input something, we have the result immediately. But as a physicist, I also want to understand what criteria, okay, based on these inputs, this neural network is actually making the decision. Okay, so one way of doing that is this is actually quite helpful. The reason that we prefer simpler artificial neural networks as the one with only one hidden layer, other than just deep learning and doing all the hard work to neural networks, is because the simple neural networks are still re-engineerable to some extent. One example will be, let's say, okay, so if it's for the change layer phase. And we can open the box. There are several ways of doing that. One way of doing is to use the rectified linear units. And then we trace back to which neuron is firing and what's the criteria of that neuron is firing. Just like when there are different neurons guiding different functions. And another one method is to just do Taylor expansion and run it on time. But for this case, for changes later, if we open up the box and look at what the neurons are doing, it turns out that it's actually very well representing the Kubo formula we have just derived right here. Remember, we trained this neural network with data that's completely breaking symmetry. So it can have quantum fluctuation. So everywhere that breaks the translation symmetry or tissue symmetry, but eventually after we have so many samples that's kind of averaged. The neuron, so the different sides on here are the different, sorry. Okay. So the value right here, for current ones are contribute the weight based on an input. And you can see that's kind of average over everywhere and kind of evenly. So it does notice the translation symmetry, despite that if in each sample it's very, very fluctuating. And also these ones are the imaginary ones of the smallest triangles. And other ones, the imaginary part of the operators for the smaller triangles. And for example, for the real part, which we also input to the neural network, it knows these values are completely irrelevant, and values are close to 1, as close to 0 everywhere. So we can do something like that. We can train on data that has the random operator, or even those we are not so certain, and the neural network handle the rest. And if we can open up the box and understand what's actually guiding the most important principles, the simple principles, then we are doing this in a completely unconventional way. Okay, so I think I'm running out of time, and with that, I thank you for your attention.
So in the classical case, you just fed the neural network samples. Whereas in the quantum case, you're using these operators, and I understand that well-chosen operators will help. But what if you just fed it samples also for the quantum case?
Thank you. That's actually a very important point I missed in my talk and lecture. As to your question, let's say if we just choose some random operators, which we thought might be important.
No, just feed it the samples. It's not even random operators.
What do you mean by deep?
What do you mean samples?
No, just as you have samples in the classical case, you can have samples.
Okay, so here's a sample. Here's a case which I use samples of the location of their electrons. And first of all, you can train a neural network. It's really, really hard to train because it thinks there's very little random information. But even if you push it through, the training through, and you throw the ball, the testing whether this is actually making sense, it doesn't make sense. That's the result. So if you train on the electron configuration of this change later introduction transition, that's the output. So it says this is zero, almost zero everywhere, and it's somewhere here for the change, supposedly change. So it's definitely not getting the universal proof for after the change later, but it's just memorizing electron density property.
So for instance, with DQMC, if you give DQMC, if you give auxiliary field configuration, it just doesn't learn. So the what kind of input you give, whether it has a relevant information for recognizing the phase, matters. With the Aizen model,
But you can give it exactly the same sort of information in the classical and the quantum case.
No. So the classical case, the configuration itself was the spins. Here, what you mean by configuration is, we have a many-body wave function, and we pick some random location. That's each instance of the variation of the Carlo. We have just a wave function, the value of the wave function.
But if you do Green's function Monte Carlo, you will.
Right. So you can just give Green's function.
Yeah.
We are not doing Green's function Monte Carlo. This is a wave function, variational wave function.
But when you do variational Monte Carlo, you can still give it just the configuration.
Yeah. So I think I understand what you're saying. So the example I showed you is right here.
I mean the value of the wave function.
Okay, so
Well, it's
here, so
exactly the same thing.
I'm not including this.
Yeah, yeah.
So if I train with alpha directly, alpha is a configuration.
Yeah.
If I train with alpha, that gives me the result I showed you that failed.
But I don't understand why it's so different in classical and quantum.
Because in classical case, the thing that determines the phase was that image itself. But in this case, what determines the phase is not the value of the wave function.
Right? Phase is very important for.
So what,
quantum
because what is a
physics.
characteristic aspect of the phase? If you have an order parameter, you give the order parameter configuration, and that's done deal.
Sure.
You're done. But we are looking at a problem where there is no order parameter. This is a topological transition where there is no order parameter. Or if you look at some out of equilibrium phases where there is no order parameter, that's when this kind of coming up with new feature selection is relevant. If you're not looking at order parameter, or even if you have order parameter, let's say your order parameter is not easily accessible given your basis that you're working at. So then instead of evaluating the order parameter or just giving the basis, you can do this feature selection, which is cheaper than evaluating the order parameter, but it is carrying the right information.
So if I understand correctly, in one of your plots you showed ground state 1, 2, 3. So you have to solve the full quantum problem and then do neural networks on top of it. I'm just curious. So you are kind of getting the ground state exactly first.
Yes. So for the fractional.
No, because we're not working on Hamiltonian.
We're not
problem.
working on Hamiltonian. This is all based on wave functions.
Right.
So that
I
was
see.
just the Laughlin thing. We had a
Oh, I see.
translator wave function qubit.
I see. Okay. Yeah, thanks.
Okay, any final questions? All right, why don't we thank Frank one more time?
Before everybody disappear, I've noticed that there are actually, our gender ratio in this school seems to be much better than in typical theory groups. I don't know why, but that's what I've noticed. And I thought maybe we'll make use of that. So tomorrow morning, we will have a table for breakfast where women are invited. No obligation if you're not interested in that kind of grouping. No offense, but if you would like to talk to other female theorists, which are very rare, you're invited to breakfast at. It's going to start at 8. Nandini promised to be there at 8. Having little kids who tend to have meltdown in the morning, likely will be late. But and my experience is that I had some 5-minute conversation with Nandini when I was just starting as a postdoc, and she doesn't even remember this. But that 5-minute conversation kept me through. I held on to it. Remaining years up until now, when I have some struggles, I remember that conversation. So you can have that kind of conversation. So that was an announcement. Let's enjoy your lunch.
And as before,